Dear students, in today's session we are going to learn about an important concept called electric dipole. To understand this, let us take the structure of the water molecule. There are two hydrogen atoms and then there is one atom of oxygen. And if you see the sharing of the electrons, you will find that in hydrogen there are total 2 electrons are there total, and then in oxygen there are altogether there are 8 electrons. So, in the entire molecule 8 electrons of the oxygen and then 2 electrons of the hydrogen, that is altogether there are 10 electrons, and those 10 electrons are shared as shown in the diagram. At the same time, there are 8 protons as well, because an atom or a molecule is always electrically neutral. Now, what we get to see here in this type of molecule, not only in water molecule, but other molecules like nitrous oxide, sulfur dioxide, hydrogen chloride, carbon monoxide, and so on. In all these molecules, the center of the positive charge and the center of negative charge, they do not coincide. Center of positive charge, see, for all the positive charges there exists a particular point where entire positive charges are assumed to be concentrated. Similarly, for all the negative charges there exists another point where all the negative charges are assumed to be concentrated. So, these are called as center of positive charge and center of negative charge, and this center of positive and negative charge, they do not coincide in all these molecules, and such molecules are called as polar molecules. So, what are polar molecules? Molecules in which the center of positive charge and center of negative charge do not coincide are called as polar molecules, and all these are example for polar molecules. We can even represent polar molecules which is something like this. So, this represent one molecule where center of positive charge and the center of negative charge. So, this is the positive charge, center of positive charge, center of negative charge, okay, minus q and then plus q, center of positive and center of negative. For no reason I have written the negative center first and then I have written positive later, okay. So, it is a random. Now, this is how we can represent a polar molecule. Not only that, a polar molecule is also one where two equal unlike point charges are separated by a certain distance. Can we say that? Two equal unlike charges are separated by a very small distance, and such system is called as electric dipole. So, all the polar molecules are example for an electric dipole. Di means there are two. So, two such poles exist, correct. So, instead of using the word pole, so two such points exist where the entire negative charge is assumed to be concentrated at one point and entire positive charge, so that what is the net charge? The net is always 0. So, that is what we are going to learn in this particular chapter, all about not the chapter, the topic, all about the electric dipole. So, what is an electric dipole? Two equal unlike point charges separated by a small distance is called as electric dipole. Now, if you take example of the carbon dioxide and then the oxygen molecule, the hydrogen, nitrogen, methane, benzene. So, in this case, the arrangement of the electrons of the oxygen and the carbon is in such a way that the center of the positive charge and the center of the negative charge, they coincide. So such molecules are called as non-polar molecules. They are called non-polar molecules. So these are the example for non-polar molecules. So molecules in which the center of positive charge and center of negative charge, they coincide, are called as non-polar molecules. So we are going to learn more about the polar molecules because our concept is electric dipole. And as you can see here, since positive center and negative center, they coincide, a non-polar molecule, they do not represent the electric dipole. Okay, so they don't form a electric dipole as such, or there is no intrinsic dipole as such. So you will understand later what I mean by intrinsic and induced dipole. So as of now, remember that polar molecules are example for electric dipoles, but definitely non-polar molecules. Non-polar molecules, yes, they do represent dipole, but under certain condition. Otherwise, in the absence of the electric field, they do not represent electric dipole. So let's see more about the electric dipole and all the terms associated with it. So refer the board and then see the diagram. So I'm going to draw an electric dipole. So this is the center of negative charge minus q. This is the center of positive charge plus q. So the line passing through these centers is called as the axial line. Axial line. Separation between the two charges is taken as 2a, and 2a is called electric dipole length. It's called electric dipole length. A is called semi dipole length. So what do you mean by semi? Half of it. That is, this is the center. So this is A, this is also A, so that the total is a 2A. Dipole length, this is semi dipole length. If I draw a line passing through the center perpendicular to the axial line, now this is called perpendicular bisector. Perpendicular bisector. This electric dipole produces an electric field. So the electric property, electric nature of an electric dipole can be measured in terms of electric dipole moment. We can measure in terms of electric dipole moment. It's a vector quantity denoted by small letter p and measured by the product of the magnitude of either of the charges, any one, q, magnitude q, into dipole length, which is 2a. So product of the charge and the dipole length will give you electric dipole moment. Accordingly, you will get the SI unit, charge in coulomb, length in meter. So coulomb meter is the unit of electric dipole moment. And we can write this in vector form. Vector p is equal to q into 2a into I will introduce a unit vector. So what is the direction of this vector? This vector is always directed from negative to the positive, like this. So vector p is along the axis, it's along the axis, and then from negative to positive charge. Okay, it's always directed from negative to positive charge. So that's the direction of the dipole moment. So remember all these terms, we are going to use them later in our derivation. So hope you have understood. So what is an electric dipole? Electric dipole is nothing but pair of equal and opposite point charges or equal unlike point charges separated by a small distance is called electric dipole. And how do we measure electric dipole moment? Product of the charge and dipole length is called as electric dipole moment. So next I am going to derive an expression for electric field produced by electric dipole at a point on the axis, at a point on the axial line. So repeatedly asked question in the board exam. So very easy derivation, listen and then see how to draw it. So let me draw a very big diagram here. So this represent an electric dipole, and I am going to always write the center of negative charge first, again for no reason, even you follow the same. This is the center of negative charge, center of positive charge. So this is the axis, axial line. Point A, point B are center of negative and positive charges. O is the midpoint of the dipole. So the value of OA is nothing but A, semi-dipole length. OB is also A. So our aim is to find electric field at a point P on the axis at a distance r from the center of the dipole. So this is important. At a point P at a distance r from the center of the dipole, that is r. So here we want to find the expression for resultant electric field produced by this entire dipole. Now why do we use the word resultant electric field? Because both negative as well as positive charges, they produce the electric field here. Now if I take a single charge plus q at a distance r, and if I take a minus q at a distance r, what is the expression for electric field? So that we have learnt in the last class. E is equal to 1 by 4 pi epsilon naught q by r square. Here also it is the same thing. Same charge, same distance. Then what is the difference? Only direction. To find the direction, place a unit positive charge plus repulsion. Therefore, this will be the direction of the electric field away from the positive charge. Place a unit positive charge plus 1 coulomb. Plus 1 coulomb is get attracted by this minus q. So, the direction is towards the negative charge. So, they differ only by the direction, but the magnitude remains the same. So, this is how we find electric field at a point. So, use the charge and then the distance to find the electric field at a particular point. So, that is what we are going to do here. So, first we are going to find the field at point P due to this positive charge. So, which I am going to write it as E plus Q. Field produced by positive charge, that is equal to 1 by 4 pi epsilon naught Q by, what is the distance from the point P till B? Because R is not the distance between the point and the charge. So, distance between the point and the charge is R minus A. So, this distance is R minus A. So, it is R minus A the whole square. What is the direction of it? To find the direction, place a unit positive charge, positive repulsion. So, it will be along this direction. Okay. So, that I am going to write along BP. BP produced means extended. Okay. Next, we will find the field at the same point due to one more charge minus q. Constant 1 by 4 pi epsilon naught. Magnitude of the charge, we do not consider the minus sign, by Now what is the distance between the point P and here? This is R plus A. So this is R plus A. So it is R plus A the whole square. Now what is the direction of the field at that point? It's a negative charge. So this positive charge is attracted towards it. So it will be like this. So this will be E plus Q. And this will be E minus Q. E minus Q. So what is the direction? It will be along PA. Along PA. So you need to write all these very clearly in the exam, otherwise they will deduct mark. So we have found the individual fields. What is the angle between the two fields? 180 degree. So what is the resultant? The resultant, whenever two vectors P and Q, they make an angle of 180 degree, the resultant is P minus Q or Q minus P, whichever is greater. Now the point here is, which is greater out of this? Based on this, you can understand very easily, the charge is the same. This is the constant. So that for value E depends on R minus A and R plus A. R minus A, see, this is a lesser value. Lesser the value of the denominator, greater is the value of E. This is R plus A. This is more than this. When this is more, this is less. So the conclusion here is E plus Q is definitely greater than E minus Q. So therefore now, how to find the resultant? So resultant is E is equal to E plus Q is greater minus E minus Q. How do we get that? Using the resultant formula. R is equal to root of P square plus Q square plus 2PQ cos theta, and when theta is 180 degree, R is equal to P minus Q. So I have used that particular form. So let's substitute here. So when I substitute here, E plus Q minus E minus Q. So for both, what is common? The common is 1 by 4 pi epsilon naught is common. Even Q is also common. So let me write Q by 4 pi epsilon naught is common. Now what is the first term here that we get? E plus Q, which is here. 1 by R minus A the whole square minus 1 by R plus A the whole square. Hope it is clear. Right. Now let's simplify this further. So that's equal to Q by 4 pi epsilon naught. You take the LCM here, R minus A the whole square, R minus A the whole square into R plus A the whole square. Okay. So what you get in the numerator is this, R plus A the whole square minus R minus A the whole square. That's equal to Q by 4 pi epsilon naught. So first see the denominator. Now just leave the power for time being here in the denominator. Now tell me what is R plus A into R minus A. R plus A into R minus A is of the format A plus B into A minus B. A plus B into A minus B is nothing but A square minus B square. So what do we write? It's R square minus A square. Correct? That is without considering the power. Correct? So now since there is a common square, so I will write that as a square. Okay. Now let's see the numerator. We have A plus B the whole square minus A minus B the whole square. That is 4AB is the value. Okay. A plus B the whole square minus A minus B the whole square is nothing but 4AB. So 4 into A is R here, into B, which is A. Okay. So that's how we get that particular step. Okay. So now we can write like this, 1 by 4 pi epsilon naught. This 4 I will write 2 into 2, and then this Q I will introduce, and then I will write A. Okay. And then I will write R, and then divide by the rest, which is R square minus A square. Okay. the whole square. Right, so there we are, E is equal to 1 by 4 pi epsilon naught into. So if you refer this term 2q into A or q into 2A, what is a q into 2A? It is nothing but dipole moment. So we can write this as a 2p r by r square minus A square the whole square. So that's the final expression for electric field at a point on the axis of an electric dipole. So identify the terms. P is the electric dipole moment, r is the distance of the point from the center of the dipole, r is the distance of the point from the center of the dipole, A is a semi-dipole length, okay, it is semi-dipole length, and 1 by 4 pi epsilon naught is nothing but a constant having a value 9 into 10 to the power 9. So this is an important derivation, and what you need to do in the exam is you have to write one more step, which is in vector form. So what is that vector form? Since electric field is a vector, do write like this: vector E is equal to 1 by 4 pi epsilon naught 2pr by r square minus A square the whole square, and then introduce a unit vector called vector P. So this is again important to write in the examination. So this is called the vector form of the electric field at a point on the axial line. Vector E 1 by 4 pi epsilon naught 2pr by r square minus A square the whole square, and then P cap. So one more special case I would like to mention here, that is, if this point is at very large distance, if point P is very far, if point P is very far, then the value of r becomes very large compared to A, and such dipole is called as short electric dipole. So what is a short electric dipole? A short electric dipole is one in which the distance of the point from the center of the dipole is much greater than the value of the semi-dipole length. And when r is much greater, r square becomes still more greater than A square, okay. When r is much greater, r square becomes still large. When r square is much larger, we can neglect the value of A square in the denominator, in that equation. So we get an expression E is equal to 1 by 4 pi epsilon naught 2pr by, neglect A square. When you neglect A square, in the denominator what we get is r square the whole square, which is r to the power 4. R to the power 4. There is already one r here, so that will get cancelled, and you will get E is equal to 1 by 4 pi epsilon naught 2p by r cube. So this is the expression for electric field at a point on the axis of a short electric dipole. Okay. How to write the same in vector form? Vector E is equal to 1 by 4 pi epsilon naught 2p by r cube. Introduce a unit vector which is p cap. So what this indicates is direction of the electric field and the direction of the dipole moment are same. So what is the direction of the electric field? It's from negative to positive, like this. Why it is in this direction? Because electric field due to the positive charge is more than that of the field due to the negative charges. This is greater. That's why it will be in this direction. The net field will be in this direction, which is same as the direction of the dipole moment, which is always from negative to positive charge. So hope you have understood this derivation. So you have to write, you have to revise, only then you will be able to understand. And we are going to learn more about this electric dipole. So we have few more derivation left, and that I am going to explain in my next class. Thank you.